Good day, everybody. We will be doing question 8 of the May-June 2022 paper 1. This is a calculus question, and it asks us to determine f prime of x from first principle. Very important, that part. And it gave us our f at x as being negative of x squared. Now, because they said first principles, we have to use this formula. And as we're now going to input our variables in here, so f at x plus h means whenever we see f at x, we are going to substitute it with f at x plus h. So it then becomes negative into x plus h all squared minus, this is our normal f at x, all divided by h. And this gives us, we still continue with the limit of h tends to 0. Let's solve for the bracket there. This gives us x squared plus 2xh minus, it has to be a plus h squared, and solving for that gives us a positive x squared. So it's a positive multiplied by a positive. We still have our h, and it's the limit as h tends to 0. Let's multiply out the negative into the bracket, then it becomes negative x squared minus 2xh minus h squared plus x squared all over h. Now, just a step back here, we multiplied out the negative and the negative. And by rules, a negative multiplied by a negative gives us a plus. Therefore, negative into negative x squared gives us a positive x squared. Now, at this step, we can already see that the positive x squared and the negative x squared cancel out. We still have the limit as h tends to 0. This cancels out, and what we are left with is the negative 2xh minus h squared. So what we can see from that, which is what we are left with, still the squared there, is that it has a common factor of h. And then what we are left with after taking out h is negative 2x minus the h. So all we did there was just to take out the common factor. This h can cancel with that h and becomes the limit as h tends to 0 of negative 2x minus h. Now, when we say the limit of this function as h tends to 0, we mean for h, it gets very, very, very close to h, but it never reaches it. But the more this becomes, the more this tends rather to 0, we are left with 2x. Important part is that after our h, so we've applied this part of the equation in that our x tends to 0, gets very, very close to 0, that it becomes nothing. After we've applied that, we need to then remove it from our equation, and then we're left with negative 2x. All right. Now, the next question they are asking is determine f at x, the prime of f at x, for our x being 4x cubed minus 5x. Now, here they didn't say anything about doing it using first principles, which would mean that we have to do it using this equation. But here we're going to do it using the normal way, the usual way of going about finding a derivative, which is to say this 3 comes down to multiply the 4, and then our x then becomes 3x to the power of 3 minus 1, minus, we do the same here, the 2 comes down to multiply the 5, and then this becomes x to the power of 2 minus 1, right? This is 12. This then becomes squared. So what we've done there is the 3 minus 1, then becoming the 2. And here this becomes 10 to the power of just x. So that is what our prime at x gives us. All right. Now, let's have a look at our final question from here. And that question is asking us to find a point 22. There is the derivative of x, where we have negative 6 and the cube root of x plus 2 all over x to the 4. Now, there is several ways to go about doing this. The best way to go about it will be in the following way. So it's the derivative with respect to x. I am going to separate out this fraction, and this becomes the cube root of x all over x to the 4 plus 2, and then it becomes x to the 4, just to separate it out so I can see it a little bit better. And then what then we have here is the negative of 6 rather, and then is the cube root of x, but let's multiply it by x to the negative 4. So the reason why we can do this is that if our exponent is below the division line, then the exponent, the power, takes a negative. And this will be the same here. All right, so let's recap on what I just did here. The negative 6 and then the cube root of x is still there. What we want is to remove the fraction, and by the powers of laws, let me write it here. It says that 1 over a to the power of n is the same as a to the power of negative n. So that's what we did in both cases. Let's just close that bracket there. Then it becomes, we want to have 1x instead of 2. So what we're going to do is say minus 6. This becomes 1 over 3, and then x to the negative 4. They are multiplying each other out. Just write that as it is. We haven't actually gotten to the derivative itself. What we are doing so far is just to make sure that it's in a form where it's easy to derive. Now, negative 6 This then becomes x because we are multiplying them, and when we multiply, remember the laws of exponents. When we multiply exponents that have the same base, what we do is we just say m plus n. We add the exponents. Okay, so let that be in the forefront of our mind. So we're going to say 1 over 3, the first power, minus the 4 plus the 2x to the power of minus 4. Haven't done anything there. And then d, the differential with respect to x. And then what is 1 over 3 minus 4? So when you go and find that out, you find that it's negative 11 over 3. And our 2 to the power, or our 2x to the power of minus 4, unchanged still. So all of what we've done before is just a little bit of algebra, making sure that we get it to a point where it is actually derivable, if there's such a word. This is actually 6 times x to the power of negative 11 over 3. Let me just rewrite down properly. Then x to the power of 11 over 3 plus 2x to the power of negative 4. Now, how do we then derive this? Same rules as we've just used now in 8.2.1. What we're going to do is to take this power, which is negative 11 over 3, multiply it by negative 6, and then we say negative 11 over 3 minus 1. So what would we do here? I take the power, bring it down to multiply the negative 6, x to the power of negative 11 over 3, and then I minus the 1 from our power here of x. We do the same here. The negative 4 comes down, becomes 2. It multiplies rather by 2, and then x to the negative 4 minus 1 again. Now, if you can see here, the dx, the differential with respect to x, it has vanished, and the reason why is because we've actually applied the derivative on this line. So we have to lose that dx because we've already applied it. And then this now becomes 22 x to the power of negative 14 over 3 plus, should be minus there because it's minus 4 multiplied by 2, minus 8, and then x to the power of minus 5. Okay, a quick recap of what we've just done. We got the dx of that particular expression there. We need to get it in a way that is derivable, and in the form that it is now, it won't be easy to derive. First thing is, I wanted to separate the fraction, and after separating the fraction, I want to remove the fraction altogether. Therefore, the x to the 4 then becomes x to the negative 4. So instead of dividing by x to the 4, I am multiplying by x to the negative 4. I do the same here. The root of the cube root of x can be written as x to the 1/3. That's the only change on that line. Now, from the laws of exponents, when we are multiplying two exponents of the same base, we add the exponents, which is what we did here, the 1/3 minus 4. So we added it, so it's 1/3 plus the minus 4. Nothing changed there. And this solves out to be -11/3. And then we plus 2 to the x minus 4. Now we apply the derivative, so it is no longer there. The power of x, which is -11/3, comes down to multiply the -6. And x to the power of what was originally there, the power that was originally there, minus the 1, plus this comes down, -4 multiplied by 2, x to the -4 minus 1, like we did with the previous part, and then it solves out to become that.